Welcome to Ultimate Sleep Doctor. Tonight, we'll be traveling to a realm of quiet wonder. Imagine a material, a substance that defies the everyday rules of electricity. Superconductors, they're called particles moving without resistance, a silent current flowing through the universe. It's a concept born of profound physics, hinting at hidden connections and the elegant dance of energy. There's a beautiful stillness within this discovery, a reminder that even the most complex systems can hold a serene order. Let your mind settle, finding peace in the idea of a world unbound by friction. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe, let your thoughts drift like clouds. Let's begin. Let's talk about a truly remarkable property of certain materials, one that's often described as almost magical. It's called the Meissner Effect, and it's how superconductors, materials that conduct electricity with absolutely no resistance, actively repel magnetic fields. It wasn't discovered accidentally. It was a careful, brilliant experiment carried out by Dutch physicist Heike Kamerlingh-Onnes in 1931 while he was studying helium-3, a very special element at incredibly low temperatures, colder than outer space. Onnes was trying to understand the behavior of electrons, the tiny particles that carry electricity at these extreme temperatures. He cooled helium-3 down to just a few degrees above absolute zero. That's minus 273.15 degrees Celsius. As he meticulously measured the magnetic field around the helium, something astonishing happened. The magnetic field simply vanished. Not just weakened, but completely gone, right at the surface of the helium. This isn't the same as simply pushing a magnet away. It's far more profound. The helium wasn't just moving out of the way, it was actively preventing the magnetic field from penetrating its interior. Imagine a tiny, invisible shield surrounding the helium, perfectly blocking any magnetic forces. This shielding effect is what defines the Meissner Effect. The key to understanding this behavior lies in the quantum world. At these extremely low temperatures, electrons in a superconductor behave in a remarkably coordinated way. Instead of moving randomly, they form what's called a superfluid. This superfluid is a state of matter where the electrons are all linked together, moving as a single, coherent unit. This linked state creates an opposing magnetic field. Think of it like this. The magnetic field tries to enter the superconductor, but the linked electrons instantly react, creating their own magnetic field that perfectly cancels out the external one. It's a beautiful, instantaneous response. The superconductor is actively pushing the magnetic field away. The strength of this effect, how effectively the superconductor excludes the magnetic field, is described by something called the magnetic field exclusion field, or sometimes the Meissner field. This field is proportional to the critical current flowing through the superconductor. Higher current means a stronger Meissner field, and therefore, a more complete exclusion of the magnetic field. It's important to note that this effect isn't just about the surface. The Meissner effect extends throughout the entire volume of the superconductor. It's a complete and pervasive response to the magnetic field. And critically, it's what allows a superconductor to levitate above a magnet, a truly unforgettable sight. The superconductor is essentially pushing the magnet upwards, held aloft by this remarkable interaction between electricity and magnetism. The Meissner Effect. a silent, powerful dance of electrons, constantly shaping and controlling the world around them. The story of superconductivity isn't a sudden discovery, but rather a slow, fascinating unfolding of understanding, built upon the careful observations of several brilliant minds. It began in Italy, surprisingly enough, in the late 1910s. Professor Alessandro Bilotti, a young physicist at the University of Bologna, was investigating the behavior of mercury when he noticed something peculiar. He was studying the thermal conductivity, how easily heat flowed of mercury, and he found that when the metal was cooled very close to absolute zero, its resistance to electrical current dropped dramatically. He published his findings in 1911, but the scientific community, largely focused on classical physics at the time, wasn't immediately convinced. Bilotti's results were dismissed, and his work faded into relative obscurity for nearly 50 years. Then, in 1961, a Canadian physicist named John Robert Campbell was working at Bell Telephone Laboratories in the United States. Campbell was investigating a new type of mercury-tin alloy, again attempting to find a material with exceptionally low electrical resistance. He meticulously repeated Bilotti's experiments, using a very similar apparatus and cooling method. To his astonishment, he too observed a significant drop in resistance at extremely low temperatures, even lower than Bilotti had achieved. Campbell's independent verification of the phenomenon, published in 1962, brought superconductivity back into the spotlight. Crucially, Campbell's research wasn't just a simple replication. He developed a more precise and sophisticated method for measuring resistance, utilizing a very sensitive resistance bridge. This allowed him to quantify the drop in resistance with much greater accuracy than Bilotti had been able to do. His work demonstrated that the effect was not a fluke, but a genuine, repeatable phenomenon. It's important to remember that Bilotti's initial observations were the foundation, but Campbell's rigorous methodology and precise measurements provided the solid evidence needed for the scientific community to take the discovery seriously. The timing of these discoveries was also significant. The 1960s saw a growing interest in low-temperature physics, fueled by advancements in liquid helium cooling technology. Liquid helium, produced by fractional distillation of air, became the primary coolant for experiments at extremely low temperatures. This provided the necessary infrastructure for researchers to explore the properties of materials like mercury and tin at the temperatures where superconductivity could be observed. It wasn't until later that scientists began to understand the microscopic origins of superconductivity. The idea that electrons could pair up and move through a material without resistance. But the initial spark, the recognition of the resistance drop, came from the combined efforts of Bilotti and Campbell, representing a remarkable example of scientific persistence and independent verification. Their work laid the groundwork for the incredible technological advances that superconductivity would eventually unlock. Superconductors aren't a single, uniform material. Instead, they fall into distinct categories based on how they interact with magnetic fields. We can broadly divide them into Type I and Type II superconductors, each exhibiting radically different behaviors. Type I superconductors, discovered first, are characterized by a very abrupt and complete expulsion of magnetic fields when they transition into the superconducting state. Think of it like a perfect shield. When cooled below their critical temperature, they instantly and completely block any magnetic field from penetrating. This behavior is governed by a simple, almost crystalline response. The electrons, moving in perfect unison, create a region of perfectly opposing magnetic fields, completely repelling the external field. These materials, predominantly pure metals like lead and tin, demonstrated this behavior with remarkable consistency. They were ideal for early applications like sensitive magnetic field detectors, but their inflexibility limited their use in more complex scenarios. However, the story of superconductivity took an exciting turn with the discovery of type II superconductors. These materials, largely composed of copper alloys like niobium titanium and yttrium barium copper oxide, YbCO, behave in a more nuanced way. They still exhibit the Meissner Effect, the initial expulsion of magnetic fields, but this expulsion isn't a complete blockade. Instead, they enter a state called the mixed state. In this state, magnetic field lines partially penetrate the material, forming tiny, well-defined channels within the superconducting structure. These channels are incredibly important because they allow for a controllable flow of magnetic fields. The crucial difference lies in the critical current. The maximum amount of current a type II superconductor can carry before reverting to its normal resistive state. Because of these channels, type II superconductors can sustain significantly higher currents while remaining superconducting. This is primarily due to the movement of magnetic flux within those channels, a phenomenon known as flux pinning. The imperfections and crystalline defects within the material act like tiny anchors, effectively trapping the magnetic field lines and preventing them from moving freely. This characteristic dramatically expands the range of potential applications. For example, high-temperature superconducting, HTS, magnets, many of which are type II, are used in MRI machines, particle accelerators, and even potentially in future levitating trains. The ability to control and channel magnetic fields opens up possibilities not achievable with simpler type I superconductors. Furthermore, the stability of the mixed state allows for the design of complex superconducting devices. Research continues to refine these materials and explore new compounds with even greater critical temperatures and current densities. The ability to manipulate magnetic fields with such efficiency represents a profound technological shift, promising advancements across diverse fields from energy transmission to medical imaging. Exploring the subtle differences between these types of superconductors ultimately revealed a much richer and more adaptable superconducting landscape. The story of superconductivity doesn't end with just exclusion of magnetic fields. It takes an even stranger turn when we delve into how electrons actually behave in these remarkable materials. At the heart of the mystery is a theory developed in the 1960s by John Bardeen, Leon Cooper, and John Schrieffer, collectively known as the BCS theory. This theory elegantly explained why certain materials, when cooled to incredibly low temperatures, lose all resistance to electrical current. It begins with electrons. You know, electrons are tiny, negatively charged particles that orbit the nucleus of an atom. In a normal conductor, like a copper wire, electrons are constantly bumping into the atoms of the material. These collisions cause them to scatter randomly, hindering their flow and generating heat. That's resistance. Now, BCS theory introduces a crucial ingredient: Phonons. Phonons aren't themselves electrons, but rather they're tiny vibrations within the crystal lattice of the material. Think of it like shaking a perfectly still block of ice. You create ripples that travel through the ice. These vibrations, these waves of energy, are always present in a solid, particularly at temperatures where they're easily excited. The key insight of BCS was that these phonons could actually mediate interactions between electrons. Imagine an electron moving through the lattice. It can disturb the atoms, creating a phonon. This disturbed phonon then interacts with another electron, effectively attracting it. It's a subtle, almost ghostly connection. This interaction isn't a simple push and pull, it's more like a gentle nudge. The phonon essentially acts as a bridge, allowing two electrons that would normally repel each other to momentarily bind together. This pairing is what BCS called a Cooper pair. These Cooper pairs are incredibly special. Because they're formed through this phonon-mediated interaction, they behave collectively rather than individually. They move through the crystal lattice without scattering because they're bound together and don't experience the same kind of collisions that would normally disrupt their flow. The beauty of the BCS theory is that it predicts the temperature at which superconductivity emerges. Below a certain critical temperature, enough phonons are present to consistently create Cooper pairs. As the temperature drops, more and more Cooper pairs form, leading to the complete disappearance of resistance. Above the critical temperature, the vibrations slow down, and the Cooper pairs break apart, restoring normal electrical resistance. The BCS theory doesn't explain everything about superconductivity. There are still unanswered questions and ongoing research. However, it provides a remarkably accurate and intuitive explanation for this astonishing phenomenon, showcasing the intricate dance between electrons, vibrations, and the remarkable ability of certain materials to conduct electricity without loss. The story of superconductivity took a surprising turn in the late 1980s, a shift so dramatic it felt like discovering a hidden world. For decades, superconductivity had been considered a remarkably peculiar phenomenon, confined to incredibly cold temperatures, typically requiring liquid helium, which is itself a rare and expensive resource. This limitation severely restricted the practical applications of these amazing materials. Then, in 1986, a team at Cambridge University, led by Robert Chang, made a breakthrough that changed everything. They were investigating a barium copper oxide compound, initially created by Jörg Bednorz and Alex Müller in a German lab, but the Cambridge team was exploring variations. They synthesized a material with a specific composition, barium, copper, and oxygen, and, astonishingly, observed superconductivity at a temperature of -173 degrees Celsius, -279 degrees Fahrenheit. This was far warmer than any known superconductor at the time, a temperature achievable with liquid nitrogen, which is much more readily available and significantly cheaper. This discovery, centered around the material now known as YBCO, the letters representing its constituent elements, sent ripples of excitement through the scientific community. The initial reaction was cautious optimism, but further research quickly confirmed the magnitude of the finding. The team meticulously investigated the material's structure, using techniques like X-ray diffraction, revealing a layered arrangement of atoms. This layered structure was key to understanding the behavior. The oxygen atoms weren't simply present. They formed a complex network interspersed within the copper-oxygen layers, creating what scientists termed clefts. The crucial element in YBCO's superconductivity wasn't just the layered structure, but the way electrons interacted within it. The researchers theorized that the oxygen atoms within the clefts played a vital role in facilitating the formation of Cooper pairs, those paired electrons that are responsible for the material's lack of electrical resistance. The oxygen atoms likely interacted with the electrons, creating a sort of highway for them to move through the material without encountering any opposition. Following the Cambridge discovery, the race was on. Scientists worldwide began synthesizing and studying other complex cuprates, materials containing copper and oxygen in similar layered structures. The goal was to find materials with even higher transition temperatures, the temperature at which superconductivity suddenly appears. Researchers found a steady stream of new high-temperature superconductors, each slightly improving upon the previous record. Some compounds achieved superconductivity at -135 degrees Celsius, -211 degrees Fahrenheit, a significant step forward. These new discoveries suggested that superconductivity wasn't limited to a handful of materials. It was a phenomenon that could be found in a surprisingly wide range of complex metallic oxides. The implications of this research were enormous. While practical applications were still years away, the discovery of high-temperature superconductors fueled intense research and development, propelling the field of superconductivity towards a future where lossless power transmission and revolutionary technologies could become a reality. The story of YBCO and the subsequent exploration of the cuprate family represents a pivotal moment in the quest to unlock the full potential of this extraordinary phenomenon. The hum of a hospital is a familiar sound, but within its walls, a truly remarkable technology quietly performs a vital task: magnetic resonance imaging, or MRI. At the heart of the MRI machine lies a colossal superconducting magnet, and that's where the magic of superconductivity truly comes to life. These magnets, often spanning several meters in diameter, generate incredibly strong magnetic fields, far stronger than any permanent magnet could ever produce. This intense field is precisely what allows doctors to peer deep inside the human body, revealing detailed images of organs, tissues, and even the tiniest blood vessels. The key is that these magnets are made with wires cooled to incredibly low temperatures, typically using liquid helium. This cooling is essential. It's what creates the superconducting state where the electrical resistance vanishes. Without this near-zero resistance, the magnet would constantly lose energy as heat, and the image quality would rapidly degrade. Instead, a constant, unwavering magnetic field is maintained, providing the foundation for the MRI scan. The scanner sends radio waves into the patient's body. These waves interact with the atomic nuclei of the body's tissues, causing them to briefly resonate like a tiny, natural antenna. The returning signals are detected and processed by the computer to generate the detailed images. Now, let's look beyond the hospital. Superconducting magnets are also essential components of some of the most powerful particle accelerators in the world. These machines, like the Large Hadron Collider at CERN, smash particles together at near-light speeds. To guide these incredibly energetic particles along a precise path, Researchers employ powerful magnetic fields. Again, the key here is superconductivity. Without it, the immense currents required to generate these fields would dissipate so much energy that the accelerator would become completely impractical. These superconducting magnets are arranged in rings, often hundreds of meters in circumference. The particles are accelerated around these rings, repeatedly colliding with a target. Analyzing the debris from these collisions provides scientists with invaluable data about the fundamental building blocks of the universe, things like the Higgs boson and other exotic particles. The design and construction of these magnets are feats of engineering. The superconducting coils are meticulously crafted from specialized materials like niobium titanium, which offers both strength and superconducting properties. The cooling systems surrounding these coils operate constantly, maintaining the temperatures required for superconductivity. The scale of these projects is truly astonishing. The superconducting magnets within the Large Hadron Collider, for example, are among the largest and most powerful magnets ever built. Their precise control and stability are crucial for the successful operation of this groundbreaking research facility. It's a beautiful example of scientific innovation, built upon the extraordinary properties of materials and the dedication of countless scientists and engineers. And it all began with the discovery of superconductivity, a phenomenon that continues to unlock incredible possibilities in medicine and our understanding of the cosmos. The world of superconductivity, once understood primarily through the elegant equations of the BCS theory, held a secret within its most sensitive manifestations. Scientists weren't just interested in the raw power of lossless current flow. They craved a way to measure incredibly small magnetic fields far too weak for conventional sensors. This led to the development of superconducting quantum interference devices, or SQUIDs, devices that essentially turned the peculiar properties of superconductors into instruments of astonishing precision. A SQUID isn't a single, massive piece of superconducting material. Instead, it's a remarkably intricate construction, usually employing a small loop of superconducting material, often niobium or titanium, threaded with a very thin wire carrying a constant electrical current. This loop is carefully positioned within a strong magnetic field. Now, this is where the quantum magic begins. Because the superconducting material experiences zero resistance, the current flowing within the loop doesn't lose energy. However, this constant current is exquisitely sensitive to any changes in the magnetic field surrounding the loop. As the magnetic field fluctuates, perhaps caused by the faint magnetic signature of a tiny biological signal or the minute movements of a particle in a particle accelerator, the current flowing through the superconducting loop changes. This change isn't random. It's directly proportional to the strength of the magnetic field. The key to amplifying this incredibly small change lies in a part called the SQUID magnetometer. The superconducting loop isn't directly connected to a measuring device. Instead, it's linked to a sensitive microwave resonator. When the current changes in the loop due to a magnetic field, this change affects the resonant frequency of the microwave signal passing through the loop. Scientists can meticulously measure this tiny shift in the microwave frequency with incredible accuracy. This measurement then translates directly into a measurement of the magnetic field that caused the change. The result is an incredibly sensitive magnetometer, capable of detecting magnetic fields on the picotesla, 10 sup 12/sup Tesla scale, a level of sensitivity that's simply unattainable with traditional sensors. The resulting instruments have found applications in a remarkable range of fields. Researchers use squids to study the magnetic fields generated by the beating hearts of mammals, to investigate the weak magnetic signatures of neurons in the brain, or to track the movements of tiny magnetic particles. In particle accelerators, squids are used to precisely control and measure the magnetic fields within the accelerator, ensuring that beams of particles travel along the most efficient and accurate paths. They're even employed in geological surveys, mapping subtle magnetic variations in the Earth's crust, providing insights into the planet's deep structure. The continued refinement of squid technology promises even more groundbreaking discoveries in the years to come, a testament to the profound and surprising possibilities hidden within the realm of superconductivity. The quest for room temperature superconductivity isn't just about creating a new material. It's about unlocking a transformation of how we generate, transmit, and utilize energy. For decades, scientists have chased the Holy Grail, a material that conducts electricity with absolutely no resistance at everyday temperatures. The current generation of high-temperature superconductors requires intensely cold conditions, often approaching absolute zero, making their practical applications incredibly complex and expensive. However, recent advancements, particularly the work with carbonaceous sulfur hydride, have ignited a renewed sense of excitement and directed research towards truly accessible superconductivity. Researchers are exploring a wide range of compounds, moving beyond just sulfur-based systems. Lanthanum superhydrides, for example, are a significant area of investigation. These materials, under immense pressure, sometimes comparable to that found deep within the Earth, exhibit superconductivity at relatively mild temperatures. The challenge here isn't just synthesizing the material, but understanding the precise mechanisms driving the superconducting state. It's believed that the hydrogen atoms within these compounds play a crucial role, forming a network that allows electrons to flow without any scattering. Beyond the chemical composition, the future hinges significantly on understanding the role of pressure. Can we find materials that maintain their superconducting properties at atmospheric pressure? Or, alternatively, can we develop techniques to apply pressure on a large scale, perhaps through advanced materials like graphene or diamond, to stabilize these compounds? It's a complex puzzle, and the answers could drastically alter our approach. The potential impacts of truly practical room temperature superconductivity are staggering. Imagine a global power grid with zero energy loss during transmission. Power plants could be located far from population centers, and electricity could be delivered anywhere in the world with perfect efficiency. This would dramatically reduce our reliance on fossil fuels and mitigate the effects of climate change. Furthermore, consider the advancements in transportation. Superconducting magnetic levitation trains could glide effortlessly at incredible speeds, powered by superconducting cables. Smaller, more powerful electric motors could revolutionize everything from electric vehicles to industrial machinery. Even the medical field stands to benefit. More compact and powerful MRI machines, easily accessible in remote areas, would become a reality. And, potentially, entirely new diagnostic tools based on superconducting sensors could emerge. The timeline for achieving widespread room temperature superconductivity remains uncertain. It's a field brimming with intense research, innovative techniques, and potential breakthroughs. While a commercially viable material might still be years or even decades away, the pursuit itself is driving fundamental scientific discoveries. The journey is as important as the destination, and each step forward brings us closer to a world powered by perfect electricity. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. The currents have quieted, the magnetic field still, and the secrets of superconductors gently fade. Allow your thoughts to drift, calm and unhurried, like wisps of cloud across a twilight sky until sleep finds you. Good night.